Section 5.1 is the start of a chapter in which we put a lot of things together. In fact, this entire semester of work is going to kind of come together in this one chapter, leading up to and including the fundamental theorem of calculus. Now, it's going to start with something fairly straightforward, I hope, and that is an antiderivative. So capital F of x is an antiderivative for little f, assuming that when I differentiate capital F, I get little f. And that relationship, that one is the derivative of another, is kind of encapsulated in something else here. And I'm going to introduce a lot of notation here. So this is the integral symbol. Integral of f of x dx equals capital F of x plus c. And let me share with you what some of these things are and mean. This is called the integral symbol. And this is the integrand. I remember being excited one time, ooh, I'm going to learn how to say some of these things in Spanish. And the name for this was integrando. And it sounded so weak. I'm like, really? I wanted something much more complex, like albondigas or something, I don't know. I had to take Spanish because I had to take a language as part of my degree. F of x, of course, is your antiderivative. And c is the constant of integration. So what's the semester-long joke that I've been playing on you guys? Did anyone pick that up? Yeah. All semester long I've been writing section 5.1, section 4.8 with an integral symbol. So now you know. Yay. Good on you. Now the funny thing is, here's the funny thing. If I can remind you of something that we looked at a long time ago, Newton's home, right? So, in fact, right here. Newton's home, in my mind, boy, that looks like a couple integral symbols. The funny thing is, that's not his notation. It was Leibniz that came up with that notation. So it's just ironic that those two symbols apparently are on his on the sides of his house. What's that? I've never even looked up Leibniz's house. Leibniz was not as popular or as well known as Newton was during his day. In fact, I think he died rather poor. But Newton died a pretty wealthy man. So I'm sure that he never saw his child at home. I think it's something architecturally. I don't know what it is, but I'm sure if you, I don't know, maybe you could Google it, right? Okay, let's. You've been noticing that? Good on you. You're one of few. So let's work with the integral symbol and understand what we need to do. Basically, you need to find an antiderivative. You need to find a function so that when you differentiate it, you can get what's in the integrand. Let me start by giving you a general rule here. And we'll talk a little bit more about some of the other rules involved in finding antiderivatives. But let's think about what we do when we differentiate. For example, if I had f of x was x to the fifth, what's the derivative going to be? Good, thank you. 5x to the fourth. So there's two things that you did in differentiating this, right? You brought this down and you subtracted 1 from the exponent. Let's reverse that process. When we integrate, say, x to the n dx, ooh, I almost forgot that. Does anyone know what that dx is called? It was just last section. Differential. That's not a bad answer. I know where that comes from. Yeah, change in x. All right. So the integral of f of x, the integral of x to the n here, well, I've got to reverse those. instead of multiplying by something, I'm going to divide by something. And instead of subtracting 1, I'm going to add 1. So it's going to be x to the n plus 1 divided by n plus 1 plus a constant. Yay. Now, of course, there is kind of an exception to this rule. When would this rule not work? Let's read. Close. N can't equal -1, because then you'd be dividing by 0. So other than that, we're in good shape. Now, there's a whole bunch of rules that help you out with integration. They're on page 282. You might want to keep your book open to those. Good question. Do you have to memorize all of them? Well, yeah. Yeah. I don't know. Do you have to answer all of them? Maybe. I don't know. What's that say? I can't hear you. I can almost hear you. Okay, all right, so you don't have to memorize all of them. A little extortion here, sorry about that. So you can memorize down to here. So secant and above, you can memorize. Now the good thing about them is this. All your rules for integrals come from your rules for differentiation. So let's think about this. What do you differentiate to get a secant squared? What derivative gives you secant squared? Derivative of what? Tangent. So there you go. Integral of secant squared is the tangent. All right. When you differentiate sine, you get cosine. So the integral of cosine is the sine. Now, it doesn't work perfect in both directions, right? Because what happens when you differentiate the cosine? You get negative sine. So the integral of sine is the negative cosine. So there's, you're not really learning much more when you're memorizing your integration rules. They're very, very similar. In fact, this page shows you both of your rules kind of side by side. Here's the derivative rule. Here's the integral rule. There's a nice almost symmetry to these things. Let's practice a few here. Page 282. Now, one of the things that I'll point out here, and this is just like our stuff with differentiation, is that when you have the integral of a sum or difference, you can split that up. When you have an integral that has a constant in it, you can factor that constant out. So I did, yes. Yeah, let me point that out now. The one last one that you should know is the integral of e to the x. Just like its derivative, the integral of e to the x doesn't change. So, in fact, yeah, there's a joke there now, right? I think I told you that one before, so I won't tell it to you. Now, the e to the x at the function party. Did you? All right. Yeah, the old saying is that math jokes, if you get them, you probably don't have any friends. So, okay, problem number 12 here. The integral of 8x cubed minus 9x squared plus 4 dx. Please get in the habit of including that dx there. It's just something I want you to do. Most of the time, yeah, you can understand what's going on and it's not going to make a difference, but there are some cases where it does make a difference. Yes, sir?
Now I'm looking at these rules. What happens when you have the chain rule involved?
Oh, great question. For integrals, you're not exactly going to see the chain rule. We're going to see something called U substitution, but with integrals, there's no product rule and there's no quotient rule. So if you have a product or you have a quotient, then you have to do a little bit of extra thinking. Because one thing you can't do is say that the integral of f of x times g of x dx, it's not the integral of f of x times the integral of g of x. You cannot break them up like that. There's no product rule. And likewise, there's no quotient rule for integrals. So we'll see when we do problem number 20, I think it is, what you have to do for stuff like that. And we're going to have to work around those obstacles. So, great question. Let me break this up. This is going to be the integral of 8x cubed dx minus the integral of 9x squared dx plus the integral of 4 dx. So all I did was I kind of distributed that integral. If you want a fancy term to impress or confuse your friends with, the integral is a linear operator. So it has these nice linearity properties. Let me go a little bit further here. Let me factor out the 8. 8's a constant. Doesn't depend on x at all, so I'll just leave in the x cubed. I'll do likewise with the 9. And I can even do it with the 4, and that leaves behind a 1 dx. Yeah, you're going to keep the dx for all three. It's just part of the notation. We don't completely understand this notation yet, but we want to get into the habit of working with it. According to this rule here, I'm going to take x, add 1 to the exponent, and divide by that same exponent. So let me zoom out a little bit, get that in here. So remember, you add 1 to the exponent and then divide by the same exponent. What would that look like for the second integral? X to the 3 divided by 3. And then the last one, let's think of it this way. What would you take the derivative of to get a 1? X. Yes, very good. You could also think of this as x to the 0 and do the same game that we do up here. Now there's one last thing that we need to include here. That is your constant of integration. Why? Well, what would happen if I differentiated a constant? What do I get? 0. So this is giving you a very general antiderivative for that function. The last thing to do here is to clean this up. 8 goes in, or 4 goes into 8 twice, so 2x to the 4th minus 3x cubed plus 4x plus some unnamed constant. And there's your antiderivative. What we're looking for is something that when I differentiate this, I get this. What's the derivative of a constant? Giselle? Derivative of a constant is 0. Let's differentiate the rest of this. Help me out. When I differentiate this polynomial, what would I get? 8. X to what power? All right, so that matches this. And then minus 9x squared. Derivative of 4x is just 4. Derivative constant is 0. Now, would it be wrong if you didn't have the constant? Not really, but I am going to be looking for it. It is a point. Don't forget the constants. It's annoying for both of us when I have to take off a point when you forget those, but please put them in. Yes, sir. You know what? Let's start skipping almost all of these steps, all right? Now I did this one out very carefully with a lot of steps just because it's the first one. But with these polynomials in particular, no, I mean, you're going to do most of these things kind of in your head. So there might be 1 or 2 steps, but not 4. Yes, sir.
For that third step, are you just writing down the power under the number?
Yeah. So you add 1 to this exponent and then divide by that same exponent. Now, you do need to take your time a little bit if some of your work, or if some of your functions get a little bit more involved, where it's not quite so easy to look at that and say, oh, okay, well, 3 plus 1 is 4, etc. Example of such would be problem number 14. Square root of x plus 1 over the 2 square roots of x dx. And let me get on the screen there. Suggestions as to how to even start this one. Yeah, let's switch it to fractional exponents. So that's x to the 1/2 plus 1/2 x to the negative 1/2 dx. Now, like I said, this one's a little bit more challenging. I'm not going to try and do all this one in my head. I am going to split it up. X to the 1/2 dx plus the 1/2 is a constant. So let me take that outside the integral. Again, I'm probably going to show you more steps than you would write down. And that's okay. You don't have to show me every little single detail. I can certainly appreciate that at this level, my students are smart enough to do a lot of this stuff in their head. The idea here is to add 1 to the exponent. So it's going to be x to the 1/2 plus 1, 3/2. So let's write this as 3/2 in the denominator. Plus 1/2, x to the negative 1/2 plus 1. What's negative 1/2 plus 1? Yeah, 1/2, 0.5. After it's all said and done, you have to include plus c. You don't have to include plus c for every integral you do. Just throw 1 in at the end. Let's clean this up a little bit. When you divide by a fraction, the trick is to invert and multiply. So it would be x to the 2/3, or excuse me, 2/3, x to the 3/2. How does this clean up over here? Yeah, the 1/2 cancels. So you're going to be left with plus x to the 1/2 plus a constant. And again, exactly how much work you need to show is up to you. I would suggest that when the exponents get a little bit more involved, that you slow down a little bit and show me some more work. 2 more here. Problem 24 and problem number 20. Quick question for you. How could I check that if I looked at that and go, you know, that just, boy, I don't know, that doesn't look right. How could you check it? Take the derivative. Isn't that cool? You can check your answers before you even hand in the test because the derivative of this should equal your integrand. It's an easy check. Make us both happy. Get it right. Problem 24. You don't always have to integrate with respect to x. Sometimes you can integrate with respect to other things. In this case, that'd be a theta. The integral of theta squared plus secant squared of theta d theta. If it helps, like our last couple problems, let's break it up. You need a d theta with both of these. That's your differential. Let's come up with some antiderivatives. What's the antiderivative here? Theta to the third divided by 3. Good. Now this one. Now we haven't really looked at our list of integral rules, but you should be able to look at that and go, oh, I know. What do you differentiate to get a secant squared? Tangent. Yeah, tangent plus the constant. Yeah, now that we got the antiderivative parts in, let's throw in the constant. Great.
I'm really worried about the constant.
It's only 1 point.
I don't know,
Yeah, I know. It's annoying. It does have its importance, and then we might see some of that as we solve some simple differential equations, but most of it you'll see much later. Liam, and then Giselle? In a lot of cases, yes. In fact, there's some problems in this section, but we're not going to have time to get there today. So if you're given some information, then yes, you'll be able to solve for the constant, and that constant will be important. Giselle?
I just want to, do you not divide
No, no. Because remember, what you're looking for is something that you differentiate to get secant squared. So if I had anything other than just tangent, my derivative would be something other than just secant squared.
Do you want us to put the constant there if there is no constant? Like for the
Uh,
like for 14?
you should, this is called the indefinite integral.
Right.
And when you're working with the indefinite integral, you're always going to get a constant. Now, it may turn out later that that constant is 0 or something else, but at least initially you should have that constant. Okay. Now this last one, long distance education, to somebody who sits in the upper left front corner of class. No, I was asking you about some rules here. There's no quotient rule. There's no product rule. There's not even really a chain rule for integrals, which is good and bad, but it leaves us with kind of a vacuum. We have to kind of work around these things. This is a really good example to kind of finish up with. Well, maybe we'll do one tiny quick one after this, but it's also a little bit of a hint as to, a problem that you're going to see on the exam. Not necessarily an integral problem, but a different problem for differentiation. What I would suggest with this is that in order to be able to move beyond this, because there's no quotient rule for integrals, we start by this. Let's divide each term in the numerator by a term in the denominator. By the way, this should be a squared here in the middle, my bad. So minus 3x squared over x to the fourth plus 5 over x to the fourth dx. You're going to get a lot of nice simplification from these terms. This is going to be a 1 minus 3x to the negative second power plus 5x to the negative fourth power dx. Now, unlike the previous ones, I'm not necessarily going to take time to write it out as the integral of 1 minus the integral of 3 times x to the negative second, etc. We're just going to integrate it from here. What do I differentiate to get a 1? An x minus 3. Now this one, let's apply our rules for integrating. Close. We're going to add 1 to the exponent. So negative 2 plus 1 is negative 1. And divide by that same exponent. So let's take a look at that again. We're going to ignore the 3. That's just going to stay out in front. Add 1 to the exponent, divide by the same exponent. Move down to the next one. Let's put the 5 here. We're going to ignore that. Add 1 to the exponent. What's my new exponent? Negative 3. And divide by negative 3. Last but not least, your favorite, the constant. So that's like the first part. We should clean this up a little bit. The negative and negative cancel each other out. I'll end up with x plus 3. X to the negative first can go in the denominator. Plus, actually it wouldn't be a plus, would it? It'd be a minus. Minus 5/3 times 1 over x cubed plus your constant. I mean, if you want to rewrite it from there, I don't care. 3 over x minus 5 over 3x cubed. Just clean it up at least a little bit on those. Just like we don't have a quotient rule, nor do we have a product rule. So our last one for today, problem number 26. The integral of the secant of y times the tangent of y minus a secant of y dy. Unfortunately, I can't split this up and say, okay, well, it's the integral of secant times the integral of this. In fact, that would actually make it worse. So what can I do? All right, what if I distributed? What if I said, all right, well, that's secant of y times the tangent of y minus secant squared of y. Does that help at all? Well, let's think about it. Is there something that you differentiate to get secant tangent? Secant. See, even though we haven't practiced them yet, you pretty much already know your rules for integration, right? Because of the opposite of the rules for differentiation. So that's going to be the secant of y. What do I differentiate to get secant squared? Tangent of y. What do I do to get the problem completely right? Plus c. Well done. All right, for homework, try 1 through 31. Tests will be on 4.3 to 5.1. See ya.